Welcome. This is the video for Lab 7, Dijkstra's shortest path. The way you would access this video is to go to Blackboard, click into your class, and click on Labs, and it's all the way, it's the very last one. Well, before we start coding or anything, we should probably talk a little bit about graphs. So what is a graph? A graph is an ordered pair. It's a set of vertices and edges. So what are those? Let's draw out a graph real quick. So if you look at this picture here, these balls would be the vertices. We'll call this a vertex. Plural is vertices, and these lines would be the edges. And all the lines in this graph is the set of edges, and all the balls in this graph is a set of vertices. Though we should probably be a little bit more accurate than lines and balls. What is an edge really? So an edge is essentially, if you think about it, what defines this line is that it has a starting point U and an ending point V. And this is what you'll see in the discrete math textbooks. You'll see an ordered pair U and V, where U is the starting point and V is the ending point. But for our particular problem, the edges actually have a cost. So, for example, they have a weight, and that represents the cost of traversing that edge. And we should probably include that in our representation of an edge and say that it's UVW. If that's what edges are, then what are vertices? The way I'd like us to think of vertices, and this is not a discrete mathematics thing, this is just for our particular problem. I'd like us to think about vertices as some label U and the set of edges E sub U, where E sub U is a subset of all possible edges. And if you think about it, that does kind of make sense, because what is a vertex? It's essentially just this label U and all the edges that U has access to. So this does make sense. And if we wanted to start talking about code, how would we code an edge? Well, maybe we could just use a struct, call it edge, and this would just be the starting point, ending point, and the weight, and that would be sufficient for an edge. How would we represent this vertex? I guess the first instinct you might have is to maybe do a struct for the vertex, where you have the label U, which is an integer, and then you have a vector of edges, which you can then access if you want to traverse from this node to somewhere else. And this is actually a pretty good starting place, but people who are much smarter than me have actually figured out a better way to do this. And I'd like to talk a little bit about that now. So what that's called is, what they've come up with is something called an adjacency list. And this is really, really big. Let's just calm down for a second. Okay, so what is an adjacency list? Essentially, you have a list of all the vertexes in your graph. So U1, U2, all the way down to U magnitude of V minus 1. And each one of these each one of these vertexes has associated with it another list, and this is a list of edges. So maybe this one has edge 1 and edge 5. This node might have edge 3 and edge 4. Maybe one of these other nodes has edge 2, and so on and so forth. And the way you would represent it in code is to have essentially like this. It would be vector of a vector of edges. And this is not too much different than what we've been talking about. So if I were to just, let me just get like a highlighter going here. Okay, so if we were to look at this, well, that sort of corresponds to the integer here. And each sort of index of this outer vector has associated with it and we'll do this one in pink, a vector of edges. And look, that's what we originally thought we might want to do. So each one of these indices represents a vertex, and each of these are the corresponding edges. And that's what we're going to do. We're going to use an adjacency list and a structure to represent our edges, and that's how we'll solve Dijkstra's shortest path. Alrighty, let's now jump into some code. I am starting from scratch, so let's give us some room here. See, what do we want to include? Let's include IO stream. We're going to need fstream. We're going to need string. We're going to need the vector library. We're also going to need the argument manager. H. Alrighty, using namespace std. So this bit of it is just set up, but I just wanted to show you that I'm starting from scratch here. Int main. Okay, so what did we talk about so far? We had some integers. We had a vector. We had edges. We had. Let's check. Hold on. So what do we get from this? We get an m, an n, an x, and a y. The m is the number of vertices, and the n is the number of edges. X and y is the starting location and the ending location. So just very quickly, what is this problem? What we're given essentially is a graph, and we have to find the shortest path between x and y. So this is the number of vertices, m is the number of vertices, n is the number of edges, x is our starting node, and y is our ending node. And we have to find the shortest path between them. What is our input file? Well, if we look at one of these input files, you'll see that here's m, n, x, and y, and then we have all of these edges that they want us to put in, where the first number is the starting point, this is the ending point, and this is the weight. And just looking at this, I can see that this is one-based indexing, so that's something we have to keep in mind. All right, let's continue implementing our code here. So we have an x and a y, and then we have a u, a v, and a w. Okay. We also want an adjacency list, vector edge. So another thing we sort of need to solve here is we need a structure like an edge. So we discussed how we're going to go about implementing that. We just said we're going to do int uvw, and we also probably want a constructor just so it's easy for us to make our edges. And B and C. Alrighty. B and C. What am I doing here? V. Okay, there we go. Oh boy, can't seem to type here. Okay, there we go. So we have an edge, we have an adjacency list, we have our vertexes, our edges, our starting point, our ending point, and our UVW, which we're going to use to build our edges. So how do we do this? First, we're going to need an input file. So let's do ifstream in file, and we'll just do this manually for now. So we'll point this to input1.txt. We're also going to need, so let's pull some of this in. So M is going to be our vertexes. I'm renaming it here just because V is less confusing. Like we know what V is when we look at the variable. Like the name is more meaningful. Then we get our edge, and then we get our X, and then we get our Y. Now we got to solve this one-based indexing problem. So X and Y are coming in with one-based indexing. And we want to keep that to where it's zero-based, because that's how our vectors work, and we want it to jive with our vectors. Now we have E. We can then get all of our edges. How would we do that? So let's just let's do a for loop. Int I equals 0, I less than E plus I. And now we can go to our in file. We can get our U, our V, and our W. So how do we add an edge to the adjacency list? Let's first talk about this. I should have mentioned this before, but we can mention it now. It's fine. So the edge that we're working on right now is called an indirect graph, and just to talk a little bit about that. Say I had a situation like this. I think I'm still in highlighter mode. There we go. So say we had a graph that looks kind of like this, and it's a triangle. And we have another graph that looks almost exactly the same, except it's an arrow. What we're saying for this first graph is that you can go from U to V, but you can't go back from, you can go from U to V, and you can go back from V to U. So this edge is like a two-way road, but this edge here is one way. So you can go from U to V, but you can't go back from V to U directly. You would have to go through this other route. And if I were to ask you, of these two graphs, which one seems simpler, you might say this first graph, because the lines look cleaner than arrows, and it's less restrictive. You can go wherever you want. But keep in mind, we have to build in that two-way functionality. And the way we would do that is to look at this graph more like this, where there's one arrow going here. Oh boy, that's a terrible arrow. Okay. There's one arrow going here. There's one arrow going back. And it's the same way for all the edges. And if I were to ask you now, which looks simpler? Is it this one or this one? Now you probably say it's a directed edge. Well, too bad we're doing indirect edge. Like that's what the problem requires. And the way to insert edges in an indirect graph is to insert them forward and backwards. So let's go and write some code to do exactly that. So edge forward is going to be UVW, and then edge backward is also going to be, well, no, it's going to be VUW, because now we're going backwards. But it's essentially the same edge. And now we have to just put that into our adjacency list. So the forward edge is going to be attached to node U. Oh boy, what is this? Forward? This autocomplete, man, it's pretty gnarly. Dot push back, and this will be the backward edge. Okay, so before we go any further, let's just see if this runs, and maybe we can print out our adjacency list. So for auto E of for auto, let's say vector of our adjacency list. Then we're going to do a nested loop auto edge of vector. And what we're going to do is cout edge.v, comma edge dot w, and let's delimit this with like some brackets here. There we go. And then over here, we'll see out. Oh, I think we might need the full index for this. So do int u equals 0, u less than v plus u. Oh, one thing we forgot. So this u, v, w, is, u and v are the u and v that we get from infile. This is all zero-based indexing. So we have to fix this, or else nothing is going to work. So u, let's decrement u, let's decrement v. So we're switching from one-based indexing to zero-based indexing. What that means is, you know how in an array the indexes are 0, 1, 2, 3. The way it's in the input file is that the vertexes start at 1, so it's 1, 2, 3, 4, which is not going to work. We want to start at 0. So now what we can do is, let's go back to our printing our thing. We can print out u, and then let's do an arrow. That might look cooler. This, and then at the end of this loop, we'll see out end line. And this will be add u now. Okay, let's see if this works. Let's see if this works. Okay, did we insert everything properly? No, we didn't. We did not. Okay, I'm going to debug this. I'll be right back. Alrighty, guys. So I did do a little bit of debugging. I think I know what the problem is. So our adjacency list here is a vector of edges, and over here we're inserting at index u, but vectors use dynamic memory. So index u doesn't actually exist yet. We can force the vector to conform to a certain size by using the resize method. So let's just do edge.resize, and how big do we want it to be? Well, we want it to hold our vertexes, so we'll resize it to the size of v, and this should work now. Oh, you can see I already tested it out. Woohoo! Spoiler alert. Okay, anyways, let's keep chugging along here. So we have our adjacency list. We know everything is working right. I think at this point we should start talking about the actual problem. We have the graph. Now we have to find the shortest path. So here's our graph, and we have to get from x all the way to y. And what's the shortest path that'll get us there? Is it this, 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 this? The first thing you do with Dijkstra is you need to set up two tables, like a list, essentially, where you take all of the nodes that you have, A, B, C, and Y, and you have two lists. The first is the first is the cost list, and the second one is the visited list. And what these lists are going to hold are two things, essentially. The cost list will hold the distance from this node to y. So A will have the distance from A all the way to y. X will have the distance x all the way to y. C will have C to y. And visited will be a Boolean. It'll be either true or false. And if you've actually looked up the Dijkstra's algorithm in other places, they have two lists. They have like a set of visited nodes and a set of unvisited nodes. I feel like that's way too complicated. You know, having one list with a bunch of booleans in it, I think makes a lot more sense to me personally. So let's add some default values, and let me do this in a really nice light color. Okay, because we want to be able to overwrite these. So initially the visited list is going to have nothing but false in it, and the cost list is going to have so here's the thing. The cost is supposed to be the distance from the node to y. We don't know what those distances are yet. So for example, over here from b to y is 12, but you could go the other route and it'll be 6. So we don't actually know what distances there are. The computer doesn't know. So let's just set them to a default value of infinity. And we're going to set them all to a default value of infinity because we don't know any of their distances except for this node. Because what is the distance between y and y? It's 0. You're already there. You don't actually need to put infinity for that one because we know the distance starting out. So we can overwrite this and say that the distance between y and y is 0. So this is the setup we have to sort of implement. So let's go ahead and do that in code, and then we'll come back and we'll talk about the loop. Okay, we'll keep this here just in case we have to debug later, the print code. So first we need an adjacency list of, not an adjacency list, just a regular vector, a vector of booleans, which we're going to call visited. Okay, and we also are going to need a vector of ints, which will be the cost, the cost of traversing, the minimum cost to get from the node to y. Also, there's this idea of infinity, which I don't think we can really achieve that. Or I'm sure there's some kind of library that would achieve it, but for our purposes, I think if we can just define infinity as 99, like some large integer, and that'll work just fine for the lab. So we have our visited, we have our cost, and we have this idea of infinity. What do we do with it? Well, we got to set the default values, and those happen to be. Well, first, we don't want the same situation to happen with our adjacency list. So let's resize them first of all. Visited, we're going to resize that to v because it's for a node, and then for the cost, let's resize that to v as well. Okay, so we avoided that bug again, and then we're going to loop. I think we already defined you, didn't we? Let's just use. Well, let's just not declare it at all. Let's just use that variable. We're not using it for anything else right now. V ++ u, and in this loop, we're going to set all of our costs to infinity, and we're going to set all of the visited to, oh, sorry about that. Oh, sorry about that. There you go. That took me a second. All right, we're going to set all of the visited to false. And the last step, if you look at our whiteboard, is to set this y to 0 because we do know that distance. So the cost of y is 0. And with that, we have completed the setup phase for Dijkstra's. Great. Let's go back here and let's talk about the loop. So the setup phase is done. We've set up Dijkstra's. What's the loop like? Well, what we're going to do is we're going to say we're looking for the minimum cost from any node to y. So we're going to say that while there exists some node p, some vertex p that where p is not visited. So all this is saying is that as long as one of these are false, do whatever is in the loop. What do we do in the loop? The very first thing we do is we have to find an unvisited vertex with the lowest cost. So get unvisited vertex. I spelled that terribly. Oh my goodness. Okay. Vertex. We're going to call this U with lowest cost. Lowest cost. The second step is to take all the neighbors of U and to adjust their cost or relax their cost. That's what it's called. They use the word relax. And I'm going to tell you what that means in just a second. Let me just write this down. So for all vertex V, it's an element of U. No, that's not an element of V. It's the neighbor of U. For all vertex for which the neighbor of U adjust that's the neighbor of U and unvisited. So and is not visited. So it can't be visited. And I'm sorry, I'm writing in all this discrete math terminology. It's just quicker. You know, I don't want to spend all my time on the whiteboard. So we're finding a vertex V that's a neighbor of U, and it's not visited. And for all of those, we're going to adjust the cost as follows. Adjust cost like so. And the way we're going to adjust the cost is that the cost of node V is going to equal the minimum, and I really hope I have enough room here, is the minimum between the current cost of V, and the cost of U plus the edge weight. The last thing we do is we mark U as visited. U as visited. So this is essentially what's happening in the loop. Okay, so this we got to put in a function. Let's just put this in a function. We're going to put this in a function. Get unvisited with lowest vertex. This is going to go in its own function, and this we can do inside the loop. So these two are going to go in their own function, and this is going to go inside the loop. Okay. Do we want to code or do we want to explain the algorithm? Let's just walk through the algorithm first, and then we'll jump into the code. So at least you know that we're not wasting our time, you know. All right. So let's see if we can actually do this. And we're in execution mode, so we'll switch to color red. So while there exists a node that is not visited, so all of them are not visited, what we're going to do, we're going to get the unvisited vertex U with the lowest cost. So that happens to be, our U right now happens to be Y. So we'll put that here. This is the one with the lowest cost. Everything else is infinity. So for all the neighbors of U that are unvisited, adjust the cost like so. Cost, blah, blah, blah. Okay. So for all neighbors, so the cost of C right now is infinity. The cost of C right now, and we're evaluating all the neighbors right now, our neighbor is C. So cost of C is infinity. The cost of U is 0, and the weight is 4. And the weight here is 4. So what's bigger? Infinity, I'm sorry, what's smaller? Infinity or 4? Well, it just so happens that that's 4. What are we going to do? You know what? Let me just rewrite this stuff in a different layer because I feel like we're going to be doing a lot of erasing and stuff like that. And I don't want to erase anything necessary. Well, let's just do like another layer. Head back to the brushes. Okay, there you go. So our U is Y, our V is C. The the cost of C is infinity, the cost of U is 0, the weight is 4. So what's smaller? Is it 4 or infinity? Well, it just so happens that it's 4. Okay, so this is 4. What's the next neighbor? The next neighbor is B. So the cost of B is infinity, the cost of U is 0, and the cost the weight, the edge weight is 12. So let's just do 12 here. What's smaller, 12 or infinity? Oh, well, it happens to be 12. Okay, so does Y have any other neighbors besides C or B? No, it does not. So let's mark Y as visited. So we'll say this is now true. All right, let's go back to the loop. Is there a node that's not visited? Yes, there is. Let's get the unvisited vertex U with the lowest cost. That happens to be C. That happens to be C. Okay. Then for all neighbors of C that are unvisited, adjust the cost. Okay, so we're relaxing. I don't like this word. Let's just cross this out and put relax. Because relaxation is what this operation is called, actually. Okay, so for all V, so what are the neighbors? Here's an unvisited neighbor. Here's an unvisited neighbor. Y is a neighbor, but it is now visited, so we don't count that. So let's do X first. What is the current cost of X? That's infinity. What is the cost of C? That happens to be 4. And what is the weight? The edge weight is 16. So 4 and 16, that happens to be 20. So what's smaller, 20 or infinity? It is 20. Okay. The next neighbor is B. And, you know, guys, it's important I show you what we're doing or how this algorithm works. Otherwise, we don't get our learning. But if you'd like, you can always skip ahead in the video. You know, that's totally fine too. But I'm going to walk through the whole thing. So B, the cost of the cost of B right now is 12. The cost of B right now is 12. The cost of U is 4, and the cost of W is 2. So what's smaller, 6 or 12? And, well, it happens to be 6. So let's just put 6 there. All right. So is that both of the neighbors of C? Yes, it is. So let's start again and check our loop condition. Are there? Oh wait, we also have to mark C as visited. So let's do that. Okay. So do we have any unvisited nodes? Yes, we do. Get the vertex U with the lowest cost. That happens to be B because C is now visited. That doesn't count. So it's either A, B, or X, and B seems to have the lowest cost. So let's go with B. So now for all neighbors of B that are unvisited, so that's this one and this one. These two are not visited. We have to relax them. So the cost of B right now is 6. The cost of U, which is going to be A, we're evaluating A right now. The cost of A is wait, I messed up here. So the cost of U, our U is B, the cost of U is 6, the cost of A right now is infinity, and the weight between B and A is 5. So 6 plus 5 is 11. Is 11 less than infinity? Why, yes it is. 11 is less than infinity. What's next here? So the next one is X. So let's now evaluate X. And I think X has a weight that's not infinity. What is the cost? The cost of X, the current cost of X is 20. The weight going from B to X is 9. So 6 plus 9 is, oh boy, it's 15. So what's smaller? 15 is smaller. So let's drop this down to about 15. Not about 15, it's exactly 15. Let's drop this down to 15. Oh, glitch. Okay, there we go. The next edge, did we do all the edges? I think so. Yeah, we did A already. Okay, so we're done with this. Let's mark B as visited. B has been visited. And let's move on to our while loop condition. Do we have unvisited nodes? Why, yes, we do. We have 2 unvisited nodes. We have to pick, the first step is to pick the smallest unvisited node that happens to be A. And for all the neighbors of A, which is, there's only really one unvisited neighbor of A, which is X, we want to relax the cost. So what is the cost of U right now? That happens to be 15. What is the cost of A right now? That happens to be 11. And what is the edge weight? That's 2. So 11 and 2. So what's smaller, 13 or 15? Well, it happens to be 13. So let's finish this. That's 13. We'll mark A now because we're on step 3. We'll mark A as visited. And the very last step is to check our loop condition. Is there at least one? Does there exist some node that has not been visited? Yes, that happens to be X. So now we are evaluating X. And we can now check the minimum cost. So for all unvisited neighbors, so this unvisited is very important. All of these nodes have been visited, so there are no unvisited neighbors. So we can just go ahead and mark X as visited. And now we go back to the loop condition. Does there exist a node that has not been visited? This condition is no longer true. So we can stop right here. So we're done with everything. And what is the product of all of these calculations? Well, the end result of doing all this is we now have this list of costs that before we didn't know these costs, but now we do. And what they represent is the cost or the distance between any given node. So this is the cost, minimum cost between node U and node Y and node, oh my goodness, I cannot type today, and node Y. So we didn't just find X, we found all of them. And for our particular problem, the only number we really need is this one. So now we have, I think, like we went through this algorithm, and we're in a position now where we can implement the remainder of the code. That is going to take some doing because I don't know if you remember, but we have to write 2 functions, one for this one and one for this. So let's go ahead and get to work here. So let's do the high level code first. So we're going to say while not all visited. We're going to do, we have to write that function. I'm aware that we haven't written that function yet. While all visited, we're going to update U to be the nearest neighbor. And then, so that's the second function we have to write. Then for all the neighbors of U. So what we can do is we can do for all edge E of in the adjacency list for U, we can go through them and implement the relaxation. So for all that are not visited, so we need an if condition to make sure that, so if not visited edge.v, then and only then do we do whatever is in here. And that happens to be, we adjust the cost. So so cost of that particular node is equal to the minimum between the cost of that node and the cost of u plus the edge weight. So that's our relaxation step. We actually don't need these brackets for that. And the very last thing that we have to do is we have to mark that node as visited. Mark the node as visited. So visited u equals true. Alrighty, so if we run this, we're going to get an error because we didn't write these two functions yet. So let's do that. Let's do that. Okay, and we can do these right under here. So first we need bool all visited, and what we're going to do is for int u equals int u equals 0, u less than. Let's do I, because I don't want to shadow. That's like a bad practice or something like that. I less than v plus I. And we can say that if visited I, if any single one of these nodes is not visited. Actually, I'm going to make this shorter. I know this is stupid, but I just want to do it. So for bool of visited, because visited is a vector, I can do this. So if any node is not visited, then we can return false. Then we can return false. Otherwise, let's return true. Okay, that should work. That should work. The last one, we have to find the int. We actually have to find the nearest neighbor. So what is the nearest neighbor? It is the unvisited vertex u with the lowest cost. Okay. So let's loop through everything in our cost vector. So for auto, no, we're actually going to need the index. We're actually going to need the index. So int I is equal to 0, I less than v plus I. How are we going to do this? So we want a vertex, and then we have a minimum distance, which will instantiate to infinity. And what we'll say is, this has to be unvisited, right? So visited I and the cost of, oh boy. So we have to compare, whatever this is, it has to be less than min dist. So we're trying to find the minimum cost. So the cost of I, if the cost of I is less than the cost of the minimum distance, what we're going to do is we're going to set the minimum distance to the cost of I, and we're going to set the vertex to I. Okay, and this will help us keep track of the vertex with the minimum with the lowest cost. And then at the end, really what we want to do is return the vertex. That should be a good nearest neighbor function. So does this work? Everything seems like it works. And what are we trying to get? What is the problem statement here? If we go to our PDF, the problem statement is we have to print out the minimum distance between x and y. So that should be easy enough. Let's just use cout for now. We'll convert this to something else later. Cout cost x. Well, what we actually did here was we worked backwards. We started at y and then we worked backwards until we found the minimum distance to x. I think that's pretty cool. Let's see if it works though. It's not cool until it works. Let's run it. Well, it says 15. What is the answer for input 1? Happens to be 15, so that works. Now what do we do? I think we should get this file ready for submission. So we have the argument manager here. We'll come down here and we'll say int argc argv, hold on, argv. Let's instantiate the argument manager argc argv. This will be am. We usually call this am. So while I'm doing this, I just wanted to say that in the spring of 2021, I was the director of tutoring for Cougar CS, and I would be remiss if I did not plug them in some way, because those guys really helped me. For those of you who don't know, Cougar CS is one of the oldest computer science clubs at the University of Houston, and at least at the time that I was director of tutoring, we were putting a lot of focus on professional development. And one of the things that we were able to do, for me in particular, is we got a lot of people internships, and myself included, by the way. I paid maybe $20 to $30 for the membership, and I landed an internship worth $15.5 thousand because of that organization. And I really do encourage you guys to check us out, because it's absolutely worth the price of membership, and a membership lasts for like a year. There's just really cool people. We also have a tutoring program which I was the head of, and we have a lot of really great talent. Let me just test it out, make sure I'm passing all the tests. Yeah, I am. Okay, great. So please check us out. Join us. You will find a link in the description for a paste bin of all of this code, and you'll also find a link to our Discord server and to our website. So thank you very much. Thank you very much for watching this video for as long as you have. I hope you were double speeding it, because it looks like it was like 50 minutes. Anyways, have a good one, guys. Thank you so much. Bye-bye.